Hi guys, I'm Aryan Agarwala. Currently, I'm a 6-star program in CodeChef and a master on Code Forces. Welcome to our channel, Learn Competitive Programming with CodeChef. Every week, we upload problem-solving tutorials, we upload tutorials in various programming paradigms, and even conduct live problem-solving sessions. So, if you want to master algorithms and data structures, then this is a one-stop destination for you. Here's a reminder to hit the subscribe button and click on the bell icon to stay notified. Today we're going to discuss a problem named linear combinations, which appeared in the December Long challenge. This is a medium hard problem, and the prerequisites for this problem are DP, which is dynamic programming, bit masking, and IEP. Okay, so let's look at the problem statement. Okay, you're given an integer sequence a1, a2, an. Find the number of integer sequences x1, x2, xn such that x each xi is between 0 and 238. No two xi are equal, so all of the x's are unique. And x1 multiplied by a1 plus x2 multiplied by a2 xn multiplied by an is divisible by 239. Now, since this answer might be quite large, computed modulo 998244353. Okay. Now, the constraints are 1 is less than equal to n is less than equal to 20. So n is very small. So the solution is probably going to be exponential on n. And AI is between 0 and 238. So that's also pretty small. Okay. So there's a hint there as well. Cool. So let's look at the sample input. Okay. So the sample input is 3, 1, 1, 1. Okay. So A is equal to 1, 1, 1. Okay. Now, there are obviously a lot of possibilities for x, right? There are 56,000 possibilities of x, but I've just put two of them over here in the PPT. So, okay, this 278, 200 is actually an example of something that's bad, okay? So 278, 200 is actually wrong because 200 into 1 is 200 plus 78 into 1 is 78 plus 200 into 1 again. So the sum is 478, right? Now 478 divided by 239 is equal to 2. Okay, so it is divisible. But the issue here is that these two x's, x1 and x3, are the same. Okay, so that's why this is not a valid sequence. The one below it, however, 57, 79, 103, this is correct, right? Because 57 into 1, so you can see 57 into 1 plus 79 into 1 plus 103 into 1, right? This is 239 and 239 is divisible by 239. So therefore this is the valid sequence, right? So here, this is the valid sequence. Okay, this is green. Yeah. Okay, so there are 103. There are 56,404 such valid sequences, and we just have to count how many there are. Okay, cool. Now, here's an observation, or more than an observation. Let's say that it's a property. Okay, that we're going to use later in this problem. So let's say we have two numbers x and y, which lie in the range 0 to 238. Okay. Now we want to find a number y such that x multiplied by y mod 239 is equal to k. Okay. Now our property states that there will be exactly one such y. Okay. Now you don't. I mean, this is a pretty basic property, but the reason for this is that there are 239 possible values for y, right? And there are 239 possible values for k. So if you can prove that x multiplied by y mod 239 is unique for each y between 0 and 238, then you're done, right? Because then I think by pigeonhole principle, all of the k's will be covered, right? Now to prove that for each y, x multiplied by y mod 239 is different, you can use this proof below. Basically assume that they're the same. Okay, for any y and m, assume that x multiplied by y mod 239 is equal to x multiplied by m. Then you'll get a contradiction saying that the difference between y and m is a multiple of 239, right? That's how modular works. So this means that either y or m is greater than equal to 239, right? And this is a violation of our range. So therefore, we can say that our property is true. Okay. Now, how does this help us? Let's say we have a sequence A that we want to find the answer for. Okay? Consider the nth element of A. If A at the nth element is equal to 0, then the coefficient of an, which is xn, the coefficient of an is xn, right? So this xn can be any value in the range 0 to 238, and an multiplied by xn will be 0 no matter what, right? So therefore an will not change the sum of the overall sequence regardless of what xn is. So basically we can just solve for the sequence between 1 and n minus 1, and at the end we can just multiply the answer for that sequence by 239 minus n minus 1. Okay, why 239 minus n minus 1? Let me just give you guys a brief explanation. So let's say we have a sequence A. Okay, we have a sequence a1, a2, a3, dot 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 an. Okay, now an is equal to 0. Cool. So what I said is that no matter what xn is, it can be any number in the range 0 to 238. Okay, no matter what xn is, the sum will be equal to 0, right? An multiplied by xn will be equal to 0 no matter what, right? So instead of solving for this sequence, we can just get the answer for the sequence a1, a2, a3, dot 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 a till n minus 1. Okay, so we can get the answer for this sequence, basically the sequence without an, and then multiply it by the number of possibilities for xn, right? Now the number of possibilities for xn was obviously 238 minus 0 plus 1, so 239. Okay, but however, remember what we said earlier, that all of the x's have to be unique, right? Now in this sequence from a1 to an minus 1, there are n minus 1 values from this range already used, right? So therefore, instead of multiplying it by 239, we'll multiply it by 239 minus n minus 1. So 239 minus n plus 1. Okay, so that was the logic for this. Yeah, cool. Now the second case is when an is not equal to 0. Okay, so for that case we can solve it in the following manner. Let us first find the number of ways of uniquely assigning x1 to xn minus 1. Okay, so what we're finding here is we don't care about the sum or anything. We just have a sequence again. We have a sequence again from a1, a2, dot 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 an. Okay. Now what we're doing is again we're excluding an from the sequence like we did earlier, and I'll show you how we're doing that. And we're saying, and this time we're not even solving for this part. Okay, we're not saying we should find the answer for the sequence a1, a2, an minus 1. Sorry, we're just saying in how many ways can we give these coefficients? In how many ways can we find the coefficients for x1, x2 all the way to xn minus 1, so that nothing like the property doesn't have to be fulfilled. Okay, and the way to do that is there'll be 239 possibilities for the first x, right? Because it can be any number from 0 to 238. Okay, now for the x2 there'll be 239 minus 1 possibilities, right? Because the one for x1 has already been used. So 239 minus 1, right? So 238, right? Now for x3 again it'll be 239 minus 2 now because 2 have already been used. So this will keep on decreasing until all the way to the end when we get 239 minus n minus 2, right? Why n minus 2 not n minus 1? Because while we're trying to assign a value to x n minus 1, n minus 2 values have already been chosen. Okay, so it'll be 239 minus n minus 2. So it'll be the product of all of these. Okay, now that's just the number of ways of assigning values uniquely from x1, x2 to xn minus 1. Okay, now the issue is the sum can be anything, right? The sum of a1 into x1 plus a2 dot x2 a2 into x2 dot dot dot, it can be anything, right? Now how do we like solve it taking that in mind? So here's the thing, let's represent the sum as k. Okay, so let's say a1 dot x1 plus a2 dot x2 all the way to a n minus 1 dot x n minus 1. Oh, and oh, we should take everything modulo 239, by the way. Okay, modulo 239 is equal to k. Okay, and so k is obviously in the range 0 to 238, right? Cool. So yeah, so let's say k is our current sum. Now we need to assign some x so that an multiplied by xn plus k mod 239 is equal to 0, right? Now, by the reason for this is pretty obvious, because if mod 239 is equal to 0, then only it means that this term is divisible by 239. Okay? So, rearranging this a bit, we need to find an xn such that an multiplied by xn is equal to um, minus k mod 239. So this is really like, if k is 0, then it's just k, otherwise it's 239 minus k. Okay, so you can look at this as 239 minus k mod 239. Okay, and this overall is some number in the range 0 to 238. Okay, now you remember what we discussed earlier in the presentation, our property, right? That if we want to find some number y such that x into y mod 239 is equal to k, where all of these are in the range 0 to 238, then there's exactly one such y. Now again, we're in the same situation, right? We want to find some xn and all numbers are in the range 0 to 238. So using our property from earlier, there will be exactly one valid xn. Okay, so this is the major thing. So what this means is that if we count the number of sequences, so if we count, I'm not going to write this whole thing. What this means is that um, yeah, we can find our answer as 239 multiplied by 238 all the way to 239 minus n minus 2, because if we assign values to x1 to xn minus 1, then xn is fixed, right? We find xn via a formula, right? It's not random, it's not like we can assign anything else to it. Okay, so really we just want to find the number of ways to assign x1 to xn minus 1 such that they're all unique, and we've already found that, right? It was 239 multiplied by 238 all the way to 239 minus n minus 2, right? Now with this whole thing, there's just one issue. Now it's given that uh like x1 x2 all the way to x n minus 1, so these are all unique, right? These are all unique values, there are no duplicates. And then we have one xn, okay, that's derived from the values we already got. Okay, but the issue is there's a possibility that xn matches one of the earlier x's we found. Okay, It could be the xn is the same as x1, it's the same as x2, or it's the same as xn minus 1. Okay, it can be any, it can match. Okay, and an example of this would be the very first thing I showed you in the presentation in the sample case, right? So let's say we're dealing with this case of 3111. Okay, so let's say we're dealing case 3111. Okay, so let's say that we want to find like a unique sequence for x1 and x2, right? So let's say we found 278. Okay, now the x3 we'll get will be 200, right? And now note that in this first set, 200 to 78, everything is unique, and in the second set, everything is unique. But the problem is that these two 200s match. That's why it's not a valid thing. So therefore, we need to find a way that so that from 239 uh, multiplied by 238 uh, all the way to what was it, 239 minus n minus 2, right? Yeah. So from this, we need to remove uh, the number of sequences where like there's some match like this. Okay. So how do we do that? Now note that all of the x from 1 to n minus 1 are still unique, right? So there is just a single clash between xn and one of the earlier x values. So let's iterate for all I from 1 to n minus 1. Okay. Now we want to find the number of sequences x where xn is equal to xi, right? So from all the sequences we found, we want to find the number of sequences where x1 is equal to where all of these are unique, but one of the xn is the same as one of these ones. Okay, that's what we're finding right now. And if we're at I, if I is 2, then we're finding the ones where xn is equal to x2, but everything else is unique. Okay. Now, if the coefficient of an and the coefficient of ai are same, meaning if xn and xi are the same, then we can do something fun. Okay. So let's say that, okay, let's take the case of n and 2 being the same. Okay. Then it means that x2 is equal to xn, right? Now the contribution of x2 and xn was like a of 2 multiplied by x2 plus a of n multiplied by xn, right? Now x2 and xn are same, so why don't we just rewrite this as a of 2 plus a of n multiplied by x2 or xn, whatever, they're both the same value, right? So this is basically the same as, how should I say, so basically finding the number of sequences where two values or more values are equal is basically the same as finding the number of sequences where, like, how should I say it? It's the same as finding the number of sequences for something like a1. So let's say it again, 2 is the one we think is equal. So let's say a1, a3, a4, all the way to an minus 1. And then at the end, we can just add a2 plus an, right? So this is a pretty uh, good way to think of it. Okay, so now we want to find the answer for this and subtract it from that 239 into 238 thing we had found. Okay, so now note that earlier the length of the sequence was n, and now the length of the sequence is n minus 1, right? So this concept is terminating, right? It'll eventually terminate. And in the case where an was 0 also, we had removed an from the sequence, right? So in that also, earlier the length of the sequence was n, and after it became n minus 1. So again it's terminating, right? Because eventually it'll reach 0 when we put some base case, right? So let's look at some implementation details. Okay, how do we actually implement this? So first of all, we have to use bit masking, okay, to represent the sequence. So this is a pretty complex topic, okay, so I won't cover it from scratch. Okay, So if you guys don't know bit masking, then you check out Geeks for Geeks or some YouTube video or something. Maybe we'll put some links in the description or something as well. But it's a well-known topic, so you'll be able to find resources for it pretty easily. Okay. So let's try a DP solution on this. Okay. So we can say that DP of some mask is equal to the number of solutions for the sequence containing all elements included in the mask, and the elements which are excluded in the mask are merged into a single element. Okay. So what this means is that so I'm going to write like a sequence in binary. So let's say we have 1 0 1 0 0 1 0 1. Okay. So that means that A1 is included, right? Because this represents A1. So this bit mask represents A1. Then A2 is excluded, right? So let's leave this. A3 is included. So A3, okay, A3 was included. Then A4 is excluded. A5 is excluded. Then A6 is included, right? So A6. Then A7 is excluded. And then A8 is included, right? A8. And there's one more element, okay? And this one more element is all of these excluded elements, okay? So 2, 4, 5, 7, okay? So A2 plus A4 plus A5 plus A7. Okay? So that's what this DP represents. Okay, the number of answers for a sequence like this. Okay? Now, um, to make, now this alone would work, okay? But just to make like our understanding a little easier, let's change it a bit. And let's say DP mask 0 represents the DP when the elements excluded from the mask sum up to 0. Okay? So in this case, we'll just ignore all of the elements outside the mask. Okay? So for DP mask 0, for DP mask 0, it's given that this last element, the sum of it is equal to, yeah, so okay, sorry, it's given that the sum of this last element is equal to 0. Okay, so we completely ignore it, okay, and we just find the answer for this sequence. Okay, now for DP mask 1, we say that the sum is not equal to 0. Okay, it's like greater than 0. Okay, so then we don't ignore it, then we solve for this entire sequence. Okay, so that's just the difference in the DPs, and you'll soon understand how this helps us. Okay, so first let's look at our base cases. Okay, so DP mask 0 where the mask contains only a single element. Okay, so what this means is that we're at a state at DP mask 0, okay, where mask has only one element. Okay, so the sequence is just equal to A1. Okay, so in this case, obviously, if you want the sum of like A1 into X1 equal to 0, then if A1 is equal to 0, then this can be anything in the range 0 to 238, right? If A1 is not equal to 0, then this has only a single value, right? Because of our property that we found. So that's what we'll do for this, okay? We'll say that if the single element A1, AI is equal to 0, then DP mask 0 is equal to 239. Else DP mask 0 is equal to 1. Okay? Now the other case is where DP mask 1 has only one element included. Okay, so what that means is that there's not one element included, where it has 0 elements included. Okay, so it has 0 elements included, so that means that it's basically representing it's basically representing A1 plus A2 plus A3 all the way to AN, right? Because no elements are included in the mask, so the only element is the sum of all the excluded elements. Okay, and again we use the concept we used in DP mask 0. Okay, so if we say that if the sum is If the sum is equal to 0, then our answer will be 239, and otherwise our answer will be 1. Okay? So yeah, the exact same thing. Now let's look at our transitions. Okay? Now, one small change we're going to make is that in the explanations I gave earlier, we looked at an as the last element, right? Okay. Now in our DPs, we're going to use something else called the LSB. Okay, least significant bit. Okay, this is going to be our last element for DP mask 0. Okay, for DP mask 1, our last element is going to be the sum of excluded elements. Okay, so this is one change, like in terminology, I want to tell you guys so you don't get confused while I'm explaining. Okay, cool. So let's look at our transitions. So the first transition we'll do is if A of LSP is equal to 0. Okay, so this is for DP mask 0. Okay, but you'll note that in all of we have two different types of transitions, and in both of them, between mask 1 and mask 0, they'll be quite similar. Okay, so first we have for DP mask 0, where A of LSP or A of N, as we did earlier, is equal to 0. So in this case, like we discussed earlier, we'll multiply 239 minus n minus 1, where n is the number of elements in the, what should I say, inside the mask, included in the mask, okay? So we multiply this by dp of the sequence without the LSP, right? So mask without the LSP, 0, okay? And similarly in dp mask 1, if the last element is equal to 0, then again we'll multiply it by sorry, that should then equal to uh sorry, no, so when the sum of excluded elements is equal to 0, then we can say we can return 239 minus n, where n is the number of elements that are included in the mask, right? So our actual number of elements in the sequence is n plus 1, which is the elements included in the mask plus this excluded element, right? But so yeah, so it'll be 239 minus n, where n is the number of elements included in the mask, multiplied by dp, I believe it's dp m0. Okay, basically what we're saying is over here we remove the LSP, right? Now in this one, we're removing all of the excluded elements, and so we're going to dp mask 0, right? Where the excluded elements don't matter. And remember earlier I told you that dp mask 0, an important case for it is that the excluded elements sum up to 0, right? So we're checking that. We're making sure the excluded elements sum up to 0 while doing this. Okay? So those are our first set of transitions. Now the second set of transitions are, so this is the case where the last element is not equal to 0. Okay? So if the last element is not equal to 0, then again we'll do something pretty similar in both. Let me just explain it to you. So in mask 0, what we'll do is first we'll find this product thing, right? 239 multiplied by 238 all the way to 239 minus n minus 2, right? And from this we need to subtract, like um, basically we need to subtract all of the sequences in which the last element, the last xn, matches one of the earlier xn's, right? What we had discussed over here. Let me just show you the presentation page so you remember it. This thing that we had, this thing that we had discussed, right? That um, this forced xn could be the same as some earlier xi. So again, this was an example I'd given. Sorry, I'd given 200, 7800, 200. So we need to handle those cases now, right? So what we had discussed is that we would iterate over all I from 1 to n minus 1, and we would find the number of sequences where xn is equal to xi, right? And we would do that by merging those two elements, right? So what we do is, for all I from, um, let's say, so LSP is our last element, right? So we'll say LSB plus 1 to n, such that I is included. So I has to be part of the sequence, right? It doesn't make sense to do it over something that's not included in the sequence only. So for all I from LSP 1 to n, where I is included, okay, what we'll do is we'll subtract from this value, right? We'll subtract dp mask without LSP and mask without I. So basically, we're merging LSP and I into our excluded elements, and we subtract dp1 from it. Okay. And similarly for dpm1, we give the same initial value 239 into 238, blah blah blah. But the only difference is that we do it till um, 239 minus n minus 1, right? Because we have that extra element at the end, right? Um, Sorry, over here I didn't close. Yeah. So we have this, and then again, so now our last element is going to be the sum of all those excluded elements, right? So now what we'll do is, for all I such that I is included, from this big value we'll subtract dp of m without I 1. So what this means is that into our whole like summation of excluded elements, now we're adding I as well, okay? We're removing I from the included elements, so we're adding it to that set of excluded elements, okay? Yeah. So that's our logic for the transitions, okay? And um, this is enough for AC, okay? So let's look at our code. So you can see the code here. So over here we're just inputting the sequence A. Over here, what we're doing is we're finding the sum for all masks. Okay, so for all masks from 0 to 2 to the power n minus 1, we're finding the sum, okay, of for all A in the mask. Okay, now two things. This LSBI is like a small thing which tells us the LSB in the mask I. Okay, and our LSBI basically just gives us the mask with the LSB removed. Okay, yeah. Now this f is basically dp, okay, but I've just called it a function f. Okay, so this is just a dp memorization thing, that if you already visited xy, then you can just return dp xy. Okay, now let's solve the dp mask 0 cases, okay, or rather we look at both together. So first are base cases, right? If RLSP x is equal to 0, meaning that if there's only one element part of the mask x, okay, then dpxy is equal to, over here, if a LSP is equal to 0, so that means that we should like, um, if a of LSP is equal to 0, if a of the only element present in the set is 0, then x can have any value, right? So that's why we return 239 in that case. Otherwise we return 1, right, because of that property we found. And similarly over here, uh, we say that if x is equal to 0, so the mask is empty, okay, so there's no included elements, there's only that big sum of excluded elements. Then if the sum of excluded elements, so this is the sum of all excluded elements, so if the sum of excluded elements is equal to 0, then we'll return 239, otherwise we'll return 1. Okay, very similar thing. Now we move on to the first transition that I mentioned, okay? If a of LSP is equal to 0, then pop count x is basically n, okay? Pop count x just counts the number of elements that are present in the mask. Okay, so then we do 239 minus n plus 1. Okay, what I showed earlier only, and we multiplied by f like dp without in the of the sequence without the lsp present, right? So dp rlspx 0. Okay, and we obviously do mod like modulo mod. Okay, and same thing down here. Okay, so if the inf sum basically is the sum of the remaining part. Okay, the sum of the uh, excluded elements. Okay, so if inf sum is equal to 0, then again we do dp xy is equal to 239 minus pop count x, which is basically n. So 239 minus n multiplied by f of x0. Okay, now that was the second transition, and this is the final transition. Okay, so first we do that big multiplication with 239, 238, etc. Okay, so over here also we did that big multiplication. And now in 0, we say for all I where I is greater than LSP, right? So I start from LSP plus 1. Okay. Now we only need to do it for I which are included in the mask, right? So this just checks that if it's not included in the mask, then we skip over it. We continue. Otherwise, if it's included, then we subtract f of x without the mask, like basically, sorry, the mask without I and without the LSP. Okay. And we do dp1 this time, obviously. Okay, and then we modulo everything at the end and we just return this dp. Okay, now similarly below you can see that we do this big 239 multiplication thing. Okay, then uh, over here first we for all I that are included in the mask, so if it's not included we skip over it. And this last time we started from lsp plus 1, right? This time the last element is the sum of all the excluded elements, right? So instead of lsp plus 1 we can start from 0. Okay, so for all I which are included in the mask, we basically subtract f of the mask without I and 1. Okay, and then we modulo tr everywhere and we say dpxy is equal to tr. Okay, and so our answer is just f of 2 to the power n minus 1, basically the mask with everything included, and 0. Okay, so let's just copy this and submit it. Oh, sorry. Yeah, my admin is counted in div2. Yeah, so while we're waiting for that to run, let's just analyze the time complexity once. Okay, now for guys who haven't done much DP analysis in the past, so the time complexity for a DP solution is equal to order of, let me just write this down, it's equal to order of states, like the number of states multiplied by the time for transition. Okay, so that's the concept. So let's look at this DP. Okay, so the number of states is equal to 2 to the power n multiplied by 2, right? So 2 to the power n plus 1, right? And the transition, so these two loops, this loop and this loop, are the big loops in transition, right? And these are order of n. So therefore, our time complexity will be 2 to the power n plus 1 multiplied by n. Okay? And yeah, so this is the right solution. Okay?